In these sections, we will begin to look at the uniaxial or longitudinal deformation and exercise how to calculate the deformation. And then we will review the one-dimensional Hooke's law, that one we've been previously introduced. So we look at this slides to formally introduce the formula for determining the longitudinal deformations. So here we assuming the cross-sectional area of this is A, assuming that is uniform throughout the whole bar. So from here we will be able to determine calculate stress equal to magnitude of P, force divided by area. And also we measured the deformation, which is the difference between the deformed model 2 and the undeformed. So delta we can measure by here. Strain is calculated by dividing deformation to original undeformed length L. Okay, and also we know Hooke's law, one-dimensional Hooke's law is related by this. So put everything together, P over A equal to E times delta over L. So move the E and L to the left-hand side, we obtain the delta equal to PL over EA. So that is these equations. We're going to exercise to calculate the deformation. And in here, you need to know a few information here. The first one is E is Young's modulus. That is a material property. And usually, you should be able to look up the data book of certain material. A is the cross-sectional area. That one you should be able to determine easily from the design or the given problem statement. The same thing L, that is the dimension here. So really in this formula, the only thing you need to determine is what is the force. Okay, so basically P is the amount, the quantity you're going to spend a little bit time in calculation. We can explain this one more. For example, we look at this schematic example here. So for this one, basically this bar is composed of uniform. Uniform, that is the cross-sectional area is different piecewise. So for example here, we call this area equal to A1, and this we have an area equal to A2, etc. And here we have an area, let me call it AM. Okay. So we can determine the deformation piece by piece. For example, for this piece, okay, for this piece, let me draw the free bar diagram here. So this is the given loading to this diagram. So that's P. By equilibrium, we can quickly determine that is a reaction here, P. So for this case, you see to fit into our model. Our model is from the previous slides here. Okay, you look at here. This is our model. Our model basically can be explained by this P and length and area A and Young's modulus E and deformation delta equal to PL over EA. So this is our standard model. Put everything into the standard model. So from here you can see this is length L. Let me call the LN, okay, and E and AN. So here for this model we fit into our standard one. So here the delta, and then we use subscript N to denote the deformation of this piece only. So for this small piece, the deformation is delta N here. Okay, so that is P L N over E and AN. Okay, similarly, and let me pick this one 2. So 2 is here. So this is the second piece, has E2 and A2, the cross-sectional area and length L2, for example. And now you can see the force applied seriously to here, so you should be able to quickly determine the force applied to the portion 2 is like this one here. Again, using our standard template like this one here, and PL over EA, so the deformation, sorry, here should be shortened. Okay, so this one should be shortened after equilibrium. This will be shortened, so this is our deformation delta set 2. So delta 2 is PL over EA, PL over EA corresponding the substrate corresponding to the second material, the second piece, the material of the second segment here. Okay, so for this case, again, this is shortened. So this is shortened. So if you like, you can have, say, recorded. So this is shortened. Okay, or otherwise, the common way we try is we simply use minus to indicate the deformation that is reduced. The deformation is negative. Negative deformation indicating its length is shortened compared to the original one. So for this model and for this model, that is positive. Okay, so if we have, let me put into this way, if we have this like this one, so basically the delta you can put into is negative PL over EA. Okay, so for this case gets shortened. Okay, so that is the way we can exercise. Okay, so now for this case, if you put everything together, and this is for this piece, it has corresponding deformation delta 1, delta, and this one has the deformation delta 2, etc., etc. So now the question is to ask what, compared to the whole thing as the whole object, I want to know what is the total displacement of point B. What is this end? How much this end going to displace? Okay, so here the total displacement of this free end, assuming this is fixed against the wall here. So to answer these questions here, this one basically you can imagine that is the summations of the deformation from each piece. Each piece contribute a little deformations, and that deformation contribute to the displacement of point B. So basically the displacement at B should be equal to the summation of all the deformation from each piece. Okay, and then here again, this is a magnitude. Okay, so here will be I equal to 1 to n, and for each delta is I, and then that is n. I equal to 1 to n is P L I E I A I. Okay, so this is the magnitude. So here we know, because everything is shortened, so the magnitude is this, and the B displaced leftward. Okay, B displaced leftward. So this leftward can be justified by observation. Okay, so here I've been trying is to disengage, to decouple the calculation of the magnitude from the sign of the direction, or the sign of whatever the attribute or negative this. Okay, so that, I think this will be the good exercise. We continue to look at, so these slides basically explain the previous one, and here is more detailed, and you can refer to for the detailed derivation here. Okay. Here we can take a look at a more practical example here, and we're going to see a numeric example for this one. So basically the general application procedure is, again, this is our standard template, I would say template for our formula P, material properties, cross-sectional area, dimension L. So deformations, delta equal to PL over EA. So to proceed the calculation of the problems, you need to take the free body diagram. Each of the free body diagram hopefully is to fit into this template. In this way, for each portions, for each free body diagram you proceed, you are able to calculate the corresponding deformation. Then you simply superpose or take summations of each free body diagrams, and then you take summation like this one. We can look at the example here. So we want to know the deformation of the steel bar. So basically here I want to see what is displacement. So let me say this is displacement B. Okay, this is A. What is the displacement of point B? Equal to how much? And at this moment, I don't know it's going to displace leftward or rightward. I don't know. So sorry, I scratched this one. Okay. So now from here, again, here is our template. Our template is P and material properties, cross-sectional area dimension delta equal to PL over EA. Okay, so that is our template here. So here you can see I'm going to take my free body diagram, a few pieces of free body diagram to fit into this template. So see what I can do. So now from here, if I say pick this portion here, okay, this portion say I exclude the point. So that is my strategy. So exclude this one. So here I want to pick this one here. Okay. So for this one, let me draw that one here. So for this one, you can see at least right now we have the loading that is 30. KIP, that means 1,000 pounds. Okay. 1 KIP, that is 1,000 pounds. So that's a kind of new definition. Okay, so that's a 30, and by equilibrium, this is 30 here. Okay, so here if you we have all the information, so Young's modulus, and then here we should be given, you will see that quickly, and A cross-sectional area, we will see that quickly, and dimension is 16. Okay, so basically we are able to determine this one. So let me, and so what is the force? So right now for this portion we have LE, but we don't know the force. Oh, force is here, 30. Okay, so for this 30, you can see it really doesn't matter. Say if I would only pick this cross section only to this one. Okay, so let me lay out that one here. So the cross section is here, so the same thing, that magnitude is 30 here. Okay, so this is our given loading 30. So you can see it really doesn't matter how you pick the cross section for your free body diagram, the loading is always 30. Okay, so basically let me draw it. So this is the displacement, and that is a 30. Okay, so this is the loading. Okay, so this is 30 KIP. Okay, now we move to this segment here. Okay, for this segment right now, my strategy, again, I pick this cross section and take this as my free body diagram. In this case, I include the second point of the loading. Okay, so that is this one here. I use dashed line to indicate where I took the cross section. So this is 30 here, and now this loading applied is included. So this is 45. Okay. So under these situations, can you see to get in force equilibrium on this cross section, this must be 15. Okay. So again, you can see if I move my selection of the cross section to here, so that would be the new free body diagram. Let me draw that one here. So in the new free body diagrams, the same thing. This is the 45, and this is 30. So the same thing here is 15 in magnitude. So from here, you can see it doesn't matter how I choose the cross section as long as confined in the segment, always the reaction is 15. So 15 as opposed to this one. So let me move to here. So here the sign convention, the upward should be go here, the downward should be go here. Okay, because they have a different direction. Okay, so this is 15. Okay, so let's move on to the next one. So next one, I'm going to have the go to the segment here in this segment. Okay, so again, my strategy, let me erase a little bit the notations. So okay, so now I pick the cross section here, and then that is the portion of the free body diagram I pick. My purpose is to calculate, to determine the direction here. So that is the cross sections. Okay, so that is the free body diagram. And right now here, this is 30, and this is the 45. And right now in this free body diagram, this load has been included, so that is 75. So from here you should be able to see, to get force equilibrium, 75 plus 30, 105, and then this is 45, so this must be equal to 60. Okay, again, you can see it really doesn't matter how you move the selection to here or to here, you can repeat the calculation, the magnitude is always 60, so that is here 60. Okay, and again the direction is on this cross section point leftward, so that must have the same sign like this one, so I moved here. Okay, so that is the magnitude, and then again in each segment, let me erase this one again. So right now you can see here we basically have 3 segments, and that segment basically each segment fitting into our templates here. Okay, and in each segment we are given the material properties, and we are given the dimension of the cross-sectional area, and we are given the length, and we already determined the magnitude here. Okay, and then we can proceed, basically see how can we proceed in calculation of this one. And these slides basically provide more detailed about the dimensions, about the size. Okay, and so that is repeated the free body diagram I just demonstrated. Okay, so that is one, and then in this illustration, the P2 equal to minus 15, P1 equal to 60, P3 equal to 30, and that is a 1 here. Okay, so here we have the sign, and based upon our analysis, and simply I define this is a negative, that is the positive. Okay, why this is negative? You can see this 15 here, basically in these portions. Okay, for example, in these portions, let me take the free body diagram stand out here. This is 15, this is 15. Are you able to see in terms of this unit is going to be deformed and compressed, which means it's going to shorten by such a loading. So that is the reasons I put the 15 downwards. Basically that is negative in nature. Okay, there's a positive. Negative indicating the corresponding deformations going to deform, shorten the material model. Okay, so that is the one here we're showing. So put into calculations, then basically we're going to determine the displacement at point D here. Okay, so that is a summation of the deformation contributed by this segment, and that is P3. That should be sorry, this is a Y here. Okay, so that is this one. Okay, and then the contribution of the deformation from the second piece, that is this one. Then accordingly the third piece go to here. And again, pay attention in this way. This calculation try to combine the magnitude as well as direction. Again, we in the first segment, if we look at the previous exam, the page here, okay, that is one here. In this segment, and that is where here. Okay, so let me pick this one. So in this segment, anywhere, that is the free body diagram. So let me pick this cross section here, and to expose this selection here. So this is a 60 we calculated by force equilibrium. This is 60. So from here you can see for this unit, it is under the stretch. The force going to stretch this material model, so that's going to induce elongated deformation. So that is the reason anywhere material point anywhere in this segment not excluded from this point. Okay, anywhere in this segment the material is under stretch and deformation. So that reason here we put into the calculation is positive here. And similar this again for the second portion is happening here. All the material in the second portion, if you are not picky, let me say not include the boundary here. Okay, just inside here, all the material point in this segment is under compression, because again from the previous slides here, and that everything is under 15 compressive. The deformation is negative, so here we put a negative here. Okay, so that's reason here again in this calculation they put together all the calculation for magnitude as well as they consider the sign. And so that is the delta. So delta, the indicating is positive. Positive, that means this point going to be displaced rightwards. That means overall this structure is going to displace rightwards. Overall the structure get elongated. Okay, their net displacement at this point going rightwards. Okay. So this is the another viewpoint of the calculation, basically simply explain what I said. And again, let me emphasize in this segment, that is our number one here in the previous slides, and that's corresponding calculations. You can see in this slide, I try to decouple the calculation of the magnitude from the telling of the sign. Okay, the second segment is here. Okay, and that one basically is based upon this one, and here that is the model, and that is the calculation. The negative sign basically shortened, shortened. Okay, in the similar process. And for the third segment here, that corresponding is this one. Okay, so displacement D relative to A, basically we can take the relative displacement equal to D relative to C relative to B, etc., like this one here. Okay, so the question, for example, if we want to calculate, say, displacement of point C, so how do you going to calculate that one? Probably you can start from here. You determine the deformation here, then this one basically equal to this. Okay, we know that this number, and C relative to B here, and we know this number that is here. You take summation together, so that is positive. So I can tell you the C going to displace to rightward, but not much. C going to displace only 20.7 mil, 20.7 thousandths inch. Okay, and this one is 75. So this is little, not that much. Okay, so And then we look at this example here. This is extreme example here. So for this case, we consider each strip as the incremental, and this let me call it dx. For each strip, for example, we can assume approximate as the rectangle. Okay. So this is the dx, and that is equivalent is our L. Okay. And then this is the force P, and assuming it has a Young's modulus and as a function of positions. So for example here there's a function of position x, okay, and has the area as a function of x. So again, the deformations at this for this case would be equal to P L equal to PL over E. That is our template. So basically that P and L equal to dx, and E is a function of x. Okay, E is the function of the positions, A is a function of the positions. Okay, so this is the small amount. So here this is the small amount of the deformation delta, and this is happen to the dx. So how about let me say that's the d delta d small amount. Okay, so here if we take the summations of all the pieces together, okay, so that is say for this piece we have the delta, for second piece we have the d delta, and for this one we have a d delta, etc. So we take the summation everything together, and then when we approach say the dx, the length this width go to 0. So basically the whole thing is going to convert into integral, and integral is p dx over e a as a function of x, and the domain is from x equal to 0 to say the whole length equal to L. Okay, so that will give us the total deformation at here. Okay, this number, if you implement this one, that will give you how much this one is going to displace. Okay, so that is the general applications to continuously changed geometry, and then to non-homogeneous, which means material properties is not the same everywhere. That we call it non-homogeneous, and for this kind of material model. Okay.